Hi, welcome to Group 12's Senior Design 1 presentation video. We are presenting the Mobile Aquatic Recorder, MAR. Presenting will be James, Roberto, Steven, Brandon, and myself, Michelle. In this presentation, we will see globalization, standards considerations, need feasibility analysis, risk analysis, multidisciplinary aspects, plan of action, personnel, budget, and end product description and other deliverables. For globalization, the MAR is designed as a globally impactful engineering solution, addressing the growing need for underwater monitoring and environmental awareness. By combining affordability and performance, our system lowers the barrier posed by expensive commercial ROV systems. To achieve proper globalization standards, the MAR must comply with internationally accepted safety and electrical standards. Thanks to its accessibility, environmental monitoring features, and educational use, the MAR has a favorable chance at expanding beyond local deployment. In regards to standard considerations, the team has considered electrical safety, waterproofing, communication reliability, and optimal system protection for the project. For the project, key standards include the FCC 15.5 for electromagnetic interference, the IEC 6529 for waterproof enclosure rating, the ISO 9022 for optical and camera reliability, and the Universal Data Interface USB-C.
Steven Seder, and I'll be presenting the feasibility analysis as well as the risk analysis. From an operational perspective, the system must be reliable in aquatic environments while maintaining ease of use. Users should be able to deploy the rover quickly, view live camera footage, and retrieve sensor measurements without complicated setup. Additionally, the device must operate for a sufficient duration, allow meaningful data collection, as well as the needs for the drive of the design toward a tethered system with continuous communication, modular sensor integration, and a waterproof enclosure capable of protecting sensitive electronics. The primary user needs would be low-cost underwater monitoring solution, easy to deploy and operate, real-time video feedback, water quality and data collection, portable and compact design, safe operation in shallow water, minimal training required. As far as the stakeholder needs go, students would be for educational learning tool, researchers and environmental data collection, and instructors, classroom demonstrations, and as well as the team, feasible senior design scope. For our risk analysis, the risk analysis identifies potential uncertainties that may impact project success. These risks include technical failures, budget overruns, scheduling conflicts, regulatory concerns, and user acceptance challenges. The team used structured methods such as brainstorming, fault tree analysis, and risk exposure matrices to categorize risks based on likelihood and severity. Continuous monitoring and mitigation strategies are implemented throughout the project lifecycle. Diving deep into the risk analysis of the key risks that were identified from feasibility analysis, and strategies were developed to minimize impact. The key points were, for the schedule, the shipping delays and procrastinations led to planned milestones and adhere to schedule. As far as the legality of things go, environmental permissions are needed, such as mental guidance and research regulations from the company that is sponsoring us, as well as professor approval. As far as the technical side of things, programming or sensor wiring errors, mentor support, and online resource testing. Economic, over budget, component mishandling led to track expenses and proper handling protocols. For our resources, skill gaps led to online courses, team training, mentor oversight. And finally, for marketing and cultural means, the low acceptance or competition would lead to market research and survey feedback.
The team can stay organized and on schedule. The plan outlines the phases, milestones, and responsibilities for each team member that is working on the project. The plan defines the scope, the timeline, and the location that the project will be worked on. By defining these aspects, the team can appropriately allocate resources to reach milestones and project completion within a time frame. As you can see for our project, it will occur between January 2026 and July 2026, in which the team will be registered for Senior Design 1 and Senior Design 2 over the course of 2 semesters. Our project covers the design, the integration of the parts, the whole integration or design, the software design and testing, and overall testing for the complete product, the prototype. This will be worked on in the FIU lab, local bodies of water, and remote for software development and programs and other work.
To start off, our project consists of 4 different types of categories: electrical engineering, computer engineering, mechanical engineering, and finally, environmental science. The electrical engineering will handle the hardware components as well as power distribution. The computer engineering will handle embedded systems. How will the operator communicate with the device? The mechanical will handle the whole design. Is the hull waterproof? And can it sustain a certain amount of pressure under a certain amount of depth? And finally, for environmental science, we will cover water quality monitoring, sensor calibration, and data analysis. In the Mobile Aquatic Recorder project, we consist of 5 team members, 2 computer engineers, and 3 electrical engineering students. We will focus on software design, hardware design, the integration of the hardware and software, and finally being able to present a prototype at the required timeline. For our budget, we broke it down into 5 phases: our research phase, our hardware phase, our software phase, our implementation phase or encasement phase, and finally, our testing and integration. To start off, our research phase is our lowest cost, because in this phase, we will focus strictly on collecting data on other products, on other designs, where these products or designs excelled and where they failed. After collecting this amount of data or information, we'll cross-reference and start a proactive risk management case where we can simply start working on our project or concept design before buying any components. After this, we will go into our hardware design. In this phase, we buy the hardware components and we start renting out the wet lab. In our software design, this is where the computer engineers focus on the programming language as well as the communication levels that we establish between the integrated control module and the operator. In our case, the integrated control module is the Raspberry Pi 4. We go into the encasement design. Now this is where we move from the interior design and go and take a step into the exterior design. We focus on the hull, the constraints that we have placed on the hull due to standards or patents. And after, we go into testing and integration. This is where we fuse the interior side and the exterior side and put it together to create a functioning prototype ready for deployment in a controlled site.
Hello, my name is Roberto Hernandez, and today I'll be presenting our end product description and other deliverables. The Mobile Aquatic Recorder is a modular, tethered, underwater robot designed to monitor water quality in freshwater and coastal environments. The system collects chemical measurements and high-definition video while maintaining communication with the operator via a 30-meter Ethernet cable. The hull will be constructed from a 3D printed plastic in order to withstand pressure, chemical exposure, and underwater conditions. Our project deliverables will be a MAR prototype system, control dashboard software, assembly and maintenance guide, field deployment results, system architecture documentation, and a final design review presentation. That will review our system specifications, testing results, and the lessons we've learned before our project handoff. In conclusion, the MAR project will address the need for affordable underwater monitoring, meet applicable engineering standards and safety considerations, demonstrate technical and economic feasibility, identify and mitigate potential risks, incorporate multidisciplinary engineering principles, and provide a functional and scalable end product. The final deliverable will be a fully operational underwater robot capable of collecting video and water quality data, supporting future improvements, and being a valuable tool for education and research. That will conclude with our presentation for Group 12.